Above you, 150 million kilometers away, a giant ball of plasma burns with unimaginable power. For 4.6 billion years, the sun has shone with steady brilliance. Not because of fire, not because of chemical reactions, but because of something far more fundamental. Fusion is the engine of the universe. It lights the stars, creates new elements, and sets the cosmic stage for life. It's the reason every atom in your body exists, from the carbon in your cells to the iron in your blood. But to understand fusion, we need to start with the building blocks of matter and the forces that hold them together. Every atom has a nucleus, a tiny cluster of protons and neutrons. Protons carry positive electric charge and normally, like charges repel each other. If that were the whole story, nuclei couldn't exist at all. But nature has a counterforce, the strong nuclear force, the most powerful force known, capable of binding protons and neutrons together despite their repulsion. However, this force only works at incredibly short distances, smaller than an atomic nucleus. To get two nuclei close enough for the strong force to grab them, they must overcome enormous electrical repulsion. That requires extreme conditions. This leads directly to the heart of fusion. If you can get nuclei close enough, they will merge and energy will be released. And the question then becomes, where in the universe do we find conditions extreme enough to make this happen naturally? In the core of the sun, temperatures reach 15 million degrees Celsius and pressures are immense, crushing enough to force hydrogen nuclei within whispering distance of each other. Hydrogen nuclei fuse into helium through a chain of reactions. But the miracle isn't just that they combine. It's that in the process, they release tremendous energy. Why? Because the mass of the fused nucleus is slightly less than the mass of the separate hydrogen nuclei. That missing mass becomes energy according to Einstein's famous equation, E equals mc squared. A tiny bit of mass multiplied by the enormous constant c squared creates a huge amount of energy. Every second, the sun converts 4 million tons of mass directly into energy through this process. And this isn't unique to our star. Fusion is the heartbeat of every star in the universe. But if the process is so powerful and so important, the next logical step is obvious. Why not recreate it here on Earth? Fusion is the closest thing we have to a perfect energy source. If mastered, it would provide clean energy. No CO2, no air pollution. Abundant fuel derived from hydrogen, the most common element in the universe. No long-lived radioactive waste, unlike fission reactors. No meltdown risk. Fusion stops instantly if conditions aren't perfect. The promise of fusion is enormous, but so is the challenge. Because while fusion naturally occurs in stars, replicating those extreme conditions on Earth is extraordinarily difficult. To see why, we need to look more closely at what fusion requires. To fuse atomic nuclei, you must overcome their mutual electrical repulsion. This requires extreme heat, millions of degrees, extreme pressure, or both. In stars, gravity provides the pressure. On Earth, we don't have that luxury. We must create these conditions artificially, and we must hold superheated matter together long enough for fusion to occur. But here's the twist. At fusion temperatures, matter becomes plasma, a chaotic soup of charged particles that cannot be contained by any solid material, because anything it touches would vaporize instantly. This means we need a way to confine plasma without touching it, and that brings us to the ingenious technologies humans have developed to tame the fire of the stars. The most popular approach to sustaining fusion on Earth is called magnetic confinement. Because plasma consists of charged particles, it can be controlled using magnetic fields. The most famous device for this is the Tokamaks, a donut-shaped chamber surrounded by powerful magnets. Inside, plasma is heated to over 100 million degrees, and magnetic fields twist it into a stable circulating loop. The goal is to create a plasma hot and dense enough, and keep it stable long enough for the fusion reactions to produce more energy than the machine consumes. Another design, the stellarator, uses complex twisted magnetic coils to shape the plasma more naturally, trading engineering complexity for improved stability. These machines represent decades of engineering, but magnetic confinement isn't the only approach, because there's another way to force nuclei to fuse. In inertial confinement, instead of using magnets, we compress fusion fuel using extremely powerful lasers. At facilities like the National Ignition Facility, NIF-192 lasers strike a tiny fuel pellet, heating and compressing it to extraordinary levels. For a fraction of a second, the pressure becomes so intense that fusion occurs. This method aims for ignition, a moment when the fusion energy released exceeds the energy required to spark the reaction. In late 2022 and again in 2023, NIF announced breakthrough experiments where ignition was achieved in isolated pulses. These results mark enormous progress, but inertial confinement is not yet a practical energy source. It's experimental science pushing the frontiers of what's possible. Both approaches, magnetic and inertial, move us closer to the same goal, making fusion energy usable on Earth. But just as interesting as the engineering is the physics underlying the fusion reactions themselves. Fusion releases energy because small nuclei become more tightly bound when they merge. Light elements like hydrogen and helium have low binding energy per nucleon. As they fuse, the binding energy increases and the difference appears as released energy. But this trend only holds for lighter elements. Once you reach iron, fusion no longer releases energy. Heavier elements must be formed by different mechanisms, such as supernova explosions or neutron star collisions. This is why stars shine only as long as they're fusing lighter elements. When they can no longer release energy through fusion, they collapse or explode. Fusion is ultimately a story about the balance between forces inside the nucleus, and how nature extracts energy from rearranging those forces. But this story leads to one more key idea. If fusion is so natural in stars, why is it so much harder on Earth? It seems paradoxical. The sun fuses hydrogen at only 15 million degrees, yet fusion experiments on Earth require temperatures above 100 million degrees. Why? Because the sun has something we don't. Gravity. An immense weight compressing its core to extreme densities. On Earth, we must compensate for the lack of pressure by raising the temperature dramatically. Higher temperature means faster moving particles, which collide more violently, increasing the chance of overcoming the electrostatic barrier. To achieve the high fusion rates needed for energy production, laboratory plasmas must be hotter than those in stars. A counterintuitive but unavoidable fact. This explains the difficulty, but also why achieving fusion, even briefly, is such a monumental scientific triumph. However, fusion is not only important for energy, it's responsible for the formation of the universe as we know it. Right after the Big Bang, the universe was hot enough for limited fusion. Hydrogen, helium, and trace elements formed in the first few minutes. Later, in stars, fusion built heavier elements. Carbon, oxygen, silicon, iron. Even heavier elements, gold, uranium, rare metals, form in supernova explosions and neutron star collisions where fusion and extreme neutron bombardment reshape atomic nuclei. Every atom in your body was forged through fusion somewhere in the universe. You are, quite literally, stardust, assembled from the remnants of long-dead stars. And that cosmic history makes the pursuit of fusion energy even more poetic. We're learning how to recreate the process that created us, but recreating it is only half the story. The other half is understanding what happens when fusion goes out of control. Fusion is often compared to nuclear fission, the process used in current nuclear power plants, but the two are fundamentally different. Fission splits heavy atoms apart. If reactions accelerate uncontrollably, they can cause meltdowns. Fusion joins light atoms together. If conditions change even slightly, temperature drops, pressure fluctuates, fusion stops instantly. It cannot run away. Fusion is inherently self-limiting. It is powerful, but safe. This safety is one of the reasons fusion is so desirable. But desirability doesn't solve the engineering nightmare. To understand where we stand today, we need to examine the current frontier. Around the world, dozens of projects chase the goal of practical fusion. The most famous is ITER, a massive international tokamak under construction in France. Its goal is to achieve sustained, net positive fusion energy. Other projects, like JET in the UK, EAST in China, and a wave of private startups, push innovative approaches, advanced magnets, alternative fuels, novel confinement geometries, and high-temperature superconductors. And while no reactor has yet produced continuous net positive energy, the progress in the last decade is extraordinary. Experiments have achieved longer confinement times, higher plasma temperatures, and more stable magnetic control than ever before. Fusion is no longer theoretical. It is an engineering challenge, one that humanity may overcome within the next few decades. But even if fusion takes time to develop as an energy source, its scientific importance remains undeniable. And that brings us to the final overarching idea. Fusion is nature's way of building complexity. It is the process that lights the stars, drives the universe, creates the elements, and shapes galaxies. It is the force that powers the sun, the engine of stellar evolution, the origin of every atom in your body, the cleanest energy source imaginable, and the frontier where physics, engineering, and cosmology meet. Fusion is the universe's masterwork, and our attempt to harness it is one of the most ambitious scientific efforts in history. To understand fusion is to understand creation itself, and perhaps one day the same reaction that lights the stars will light our cities.